This video is going to review 10.6, which talks about finding segment lengths in circles. So if you want to take a piece of paper out and try this along with me, you may. All you'll need for this is something to write with, a compass, which you can find in the student supply cabinet, and a ruler. If you'd rather watch, that is your choice as well. What I've done here is I've drawn a circle, and so it's asked you to draw 3 different circles. One of these will be fine. With each of these circles, I want to draw 2 chords that intersect each other. I don't care how you draw it as long as you don't use the diameter as one of the chords. It just ruins the wow factor, I guess we'll say, of this. So I'm going to do, let's see, I like that one right there. That works for me. So I'll do that. And don't mind my marking here. Alright, I'm going to make another chord as such right here. So, now that I have these 2 chords drawn, I want to measure each of the segmented chords. There's 4 of them in all. So I'm going to measure this guy right here. And let's give these some names so that you can see them a little bit better here. So, notice this is not the center of the circle. I want to measure AE, EB, EC, and ED. So take a moment and do that, and we'll take a look at what we have. Here are my measurements of what I ended up with. Take a moment looking at my relationship, or the one that you've drawn, and try to determine if there's any type of relationship you see between each of the segments of the chords. This one might be hard to see. Think about how I could manipulate the 3 and the 5 so that I may end up with the same idea of a 6 and a 2.5. What you may notice is that this 6 is double this 3, and this 5 is double this 2.5. Now that's just a unique relationship. Yours probably doesn't have that. But what's important about that is that if I took this and divided it, and I took this and divided it, I'm still going to, or I'm sorry, if I went from this smaller 3 and I doubled it, and I went from this and took it in half, I end up with the same product. 3 times 5 is 15. And since I took away the same multiple here, 6 times 2.5 will also give me 15. And this is our first relationship. Any 2 chords that intersect on the interior of a circle, then the product of the lengths of the segment of one chord will always equal the product of the lengths of the segments in the others. So in this particular general example, EA times EB, the product of those segmented chords, will equal the product of EC and ED, those segmented chords. So the chords' products will always be equal so long as they intersect one another. Based on that theorem, take a look at this example. If I wanted to find the missing value of x here, I know that the product of 6 times 3 will always equal the product of 9 times x. 6 times 3 equals 9 times x, which means 18 equals 9x. Therefore, x must equal 2 here. The length of that must be 2 in order for this to work. Example 2 is a little more in-depth. If you'd like to give it a try, please pause and press play when you're ready. My setup here is going to be segment x and segment x plus 4. That product will equal the segment of x plus 1 and x plus 2. Now I have a little bit of algebra to work ahead of me. Left side I want to distribute, so I get x squared plus 4x. On the right side I will FOIL, and I end up with x squared plus 3x plus 2. I skipped the O and the I step and combined them myself. Noticing here that the x squareds are on either side of the equation, they will cancel each other out. We can take a breath of fresh air there. No quadratics, no factoring here. Subtract the 3 from both sides, we're going to get an x value of 2. And therefore, I'll know all my lengths here of my circle will be 2, 2 plus 4, 6, 2 plus 1, 3, 2 plus 2, 4. 2 times 6 is 12, 3 times 4 is 12. That would be a checkmate, and we're good to go. Another relationship here has to do with 2 secant lines that intersect on the outside. So if 2 secant segments share the same endpoint outside of the circle, notice I'm talking about outside of the circle, then the product of EA times EB, so the smaller outside segment of EA and the long segment EB will equal EC times the longer segment ED. Based on this theorem and the example that I have filled in here, I know that the length of EB, well, let's start with EA. EA length is X, we don't know it. EB is unknown at this time. EC, though, I have given you as 2, and ED I have now given you as 12. Notice that it's 12 here. So, it's going to be the outside segment times the entire segment. So X times X plus 12. Notice it wouldn't be X times 12. X plus 12 is the length of EB, equals the length of EC, so the outside portion, which is 2, and the inside portion. Do not write 20 here. The length of ED is 12. So, on this side, I get x squared plus 12x equals 12 times 2 is 24. We can gasp for a minute because this will be a quadratic equation. And I subtract 24 from both sides. X squared plus 12x minus 24 equals 0. And thus I would solve this quadratic here. Now for this particular equation, this quadratic does not work out to a nice, even factorable problem. So we won't continue solving this. We'll look at another example that hopefully will be much more successful than this one. Try these two examples in terms of setting them up, and then press play when you're ready to solve. So in this example, I have 9 times 20, so the outside segment times the entire segment equals the outside segment times the entire segment. So 9 times 20 is 180. This is going to give me 100 plus 10x. Now we're fortunate in this problem we don't have a quadratic to deal with like the previous one. Subtract 100 from both sides, I get 80 equals 10x, therefore x equals 8. In the second example, same situation. It will be 4 times 9, so 4 times the entire length of 9 equals 3 times the entire length, 3 plus x. Upon solving this, I get 36 equals 9 plus 3x. 3x equals 27. And then x would equal 9 in this case. Feel free at any time during this video to rewind and replay any problems that we have walked through here. Our final theorem here talks about tangent-secant segments. If a secant segment, so that's ED in this case, and a tangent segment share an endpoint outside the circle, then the tangent segment squared, notice the quantity squared, will equal the product of EC, the outside portion, and the entire portion. So if I give you this length of 3, this length of 10, and this length of x, I can find the lengths of EA, EC, and ED pretty easily. EA would be 10, and EC is 3 as my given. To find ED, I would take my tangent segment and square it, and it will equal 3 times my entire segment, 3 plus x. Well, 10 squared is 100, and this ends up being 9 plus x. Solving this would give me 91 equals x, and that would be it. No, I messed something up. Let's go back and check this out. What did I not do? I didn't distribute my 3 correctly. So, when you multiply the 3 out, I get 3 times 3 is 9. This is a 3x. 91 equals 3x. And upon solving that on both sides, I will get a decimal here. I'll get 30 and a third. 30.3 repeating. There's the value for CD. A couple more examples using this here. Again, my tangent segment is 20, so my tangent segment squared will always equal the outside segment of my secant times the entire length of my secant, so 8 plus x. Solving this, I get 20 squared, that's 400, equals 64 plus 8x. We're going to solve this by subtracting 64 on both sides. 336 equals 8x. Therefore, x will equal a grand total of 42. Feel free to pause the video for this next example so that you can try it yourself before I go over it. So here's my setup for this problem. I'm going to distribute that 8. Again, do it correctly, unlike I did in that previous problem. 64 plus 8x. Here I'm going to subtract the 64 on both sides. A red flag should be coming up at this time. Divide both sides by 8. And negative 55 divided by 8 is a negative 6.875. And you should be stopping this problem now and wondering, what's wrong? Why did I get a negative answer? Why on this video did we just get a negative answer? And the correct answer to this question is, this tells me that this possible drawing is physically impossible to draw. It is, notice this is not to scale, these are duplicates of each other. It is physically impossible to draw a tangent segment of 3, notice how small it is, and have a secant of 8 go inside of the circle. The 8 would have to go there or outside. This is not a possible drawing. And so the solution to this, because I got a negative length, is not possible, not applicable, no solution, something like that. If you have your formula sheet handy, please take a look at it here, as all the formulas discussed in this video are described here. So the discussions today, our first one talked about the lengths of two chords. That would be this theorem here under two chords. Tangent secant, this was the one we just went over. Keep in mind that if you get a negative answer, that means that drawing is not possible. That drawing is not possible, and so that is a possible solution to one of your problems. So tangent secant, there is the formula for it, and two secants we are going to talk about, and you can take a look at the discussion that's there. Notice in the two secant example that it's written a little differently than what we had in our notes, but nonetheless it has the product of the outside secant and the entire secant equals the outside secant and the entire secant.